Good day, Math 30-1s. We are starting a brand new unit today, this one called trigonometry, and this unit is going to take this triangular trigonometry and build on the circular trigonometry that was introduced in grade 11 and take it to a whole new level. What we are talking about in chapter 4 to start is angles and angle measures. The one thing that's interesting about your graphing calculator is that it always had two different modes. It had an initial radians and it had degrees. And since the beginning of sort of time with trig, you're always told, make sure you change your calculator to degree mode. And for the first time in this course, we're going to be using radians. What is a radian? Well, we are going to be sketching angles in standard position. So we're going to be talking about degrees and something called a radian. We're going to convert between the two. We're going to talk about angles and something called coterminal angles. We'll talk a little bit about arc length and continue this discussion of circles. To start things off, we'll talk about what something called a radian is. Now, when we talk about measuring length, we can measure in different things like meters and feet and miles and centimeters. They both measure length. Now, radians and degrees are both ways to measure angles. So if I were to do a 360, this would be a full rotation in degrees. When it comes to radians, if I were to do a full rotation, I would do what's called 2 pi. And this is a number that is directly related to a circle, and it is something that we sort of accept as being true. But radian is for full rotation 2 pi. Now, when you're looking at angles being given, if no units are written, then radians is assumed. So if I looked at these two measures and I saw 60 with that little circle up there, I know that this is 60 degrees, and I see 7, and this means 7 radians. Now right now we have no idea what 7 radians is, but we could probably compare it to about a 2 times about a 3, which is close to a 6. So this is probably a little bit more than a full rotation. But right now, again, that number 7 probably doesn't mean a lot. Now, as I said, one full rotation is supposed to be 2 pi. And this is something that we sort of accept as fact. 360 degrees is 2 pi. I like to often compare those two by dividing both of those in half and saying half of 360, half of 2 pi is pi. Now, this top one in this chart, 180 degrees is pi radians, is one that I like to work with only because there's no extra number in front and the less numbers the better. This pi is still your 3.1415926 and so on, but this is the equivalent of 180 degrees, half a rotation. We could continue dividing in half to build more relationships, like half of 180 is 90, half of pi is pi over 2. Half of 90 is 45, and a half of pi over 2 might feel a little bit tricky. So let's go back up to the 180 and say, let's divide it by 4. And what you have is pi divided by 4. So when you see 45, that's equivalent to pi over 4. Right now those feel like there's something you'll never remember, but within about a day or two, you'll actually, fortunately and unfortunately, sort of have them in your brain. 60 degrees, maybe we go back to the 180 and we say, well, that's divided by 3. Pi, that's divided by 3. From 180 to a 30, that's a divide by 6. So maybe pi is divided by 6. I do promise that these will stick in your brain at some point. But each of these can be created from 180 degrees, or if you needed, 360. Now we are going to build something bigger to help remember this stuff, and what we're going to do is examine trigonometry like we did last year in a circle. We're going to continue with this idea of rotating from a fixed initial arm on the positive x-axis, so this is sort of our 0 degree angle. We're going to rotate around in a positive direction, adding every 30 degrees to start. So 30 degrees is a third of a full 90 degrees. So what we'll do is we'll deal with a degree and a radian measure. So 30 degrees is pi over 6. I'm going to start with degrees and make that really clear, and then I'm going to add the radians in a moment. But after the 30 degrees, we'll do another 30 degrees and say this should be about 60 degrees. The next one is your 90 degree angle. Add another 30 and you'd have a 120. Add another 30 and that's about a 150. Right across the other side, half of a full rotation is 180, and you keep going. 210, 240, 270, 300, 330, and technically back to 0 degrees, or 360. Now, I'll do this in a bit of a different color as we work our way around in radians, but we should be able to determine all these values with quite a bit of confidence. I'm going to be reducing some fractions as I go, but I'm going to not be counting 30s. I'm going to be counting 1 pi over 6, and then 2 pi over 6. Notice what I write though. 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and lastly 12 pi over 6, or a full rotation 2 pi. This is kind of crucial in order to have some confidence in dealing with angles in radians and degrees. Let's slide on and see if we can do this with 45 degrees, which the connection to it is pi over 4. So again, we'd have our 0 degrees in our initial arm position, but as we rotate around in degrees, we have our 45, our 90. You'll get this eventually, 135, your 180, your 225, 270, and lastly your 315 degrees. I always remember that because we're sort of adding 90 degrees from 45 to this one, we're adding another 90 degrees from here to here, we're adding another 90 degrees from here to here. It's almost like we're adding 100 but 10 less. So I see the 45, and then I see 135, and then I see 225, and then we see 315. That 10's position is decreasing by 1 each time. So there is a pattern in our position of 10. So as we do our 45 degree pi over 4, we keep adding this time pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, or pi, 5 pi over 4, 6 pi over 4, 7 pi over 4, and lastly your 8 pi over 4. Now there's many ways that we could be counting these fractions. You could be counting pi over 4s. You could be counting 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. You could be counting 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, and of course 6 pi over 3 if you're counting 60 degree angles as you work around. You could count 1 pi, 2 pi. There are a lot of fractions, and your confidence with adding fractions does help if you are very, very strong. So we've talked briefly about what a radian is, and it's just some measure to compare two angles, but we don't fully know where it's going to go just yet. There's lots more to talk about before that. In converting, not everything is always going to be a 45 and a 240. Sometimes we are going to get some messier values. So I'll start off with one that's maybe a little bit convenient, and then maybe I'll try one that's a lot less convenient. So if I were to say 45 degrees, how many radians is that? We could set up a little bit of a proportion, and I like to do mine a little bit differently, and I like to start with the fact that 180 degrees is pi radians. I like to write a line on top of each, and write the 45 degrees on the degree side, unknown radians on the radian side, and do a little cross multiply. This would move the pi up here, and we would get our x by itself by saying 45 pi over 180. Now, if you reduce the fraction 45 over 180, and most people would probably just type in 45 divided by 180 in their calculator, ignore the pi, just pretend it's not there, and then just do an answer back into a fraction. If you can do that confidently, you see a 1 over 4, and you put the pi back in, and you of course get pi over 4, which is our 45 degrees. Now there is an exact answer and a rounded answer, so if you do type into your calculator pi divided by a 4, a number actually does come out. So in our calculator, if we do type in, and I'll do this at the same time, if you do type in a pi divided by 4, what does come out is a 0.785. So if we were to call this a bit of a rounded answer to the nearest hundredth, maybe we'll call it a 0.79. So 0.79 radians is about 45 degrees. I don't really like to remember values like that, but I can confidently say that pi over 4 is 45 degrees. 240, this is one that we can try, but I might actually try to do one that's a little less nice. What if I were to pick something that isn't a nice rotation on a 30, a 45, a 60, or a 90? And what if I pick something like 35 degrees? Not as nice a number, not going to be a very good fraction. So what we would end up with is our 180 degrees is pi radians, line on top of each, 35 degrees on the degree side, unknown radians on the radian side, and a cross multiply gives us 35 pi over 180 degrees. And again, in your calculator, if you do type in, ignoring the pi, 35 divided by 180, turn that answer back into a fraction, 7 over 36. So you can say 7 pi over 36, or as a decimal, 7 pi over 36 times a pi, you'd end up with about a 0.61 radian. So answers can be convenient, answers may not be convenient. But that is a nice way to convert from degrees to radians. If you're going the other direction, the good news is the same approach could apply. If I say 180 degrees is pi radian, and I want to turn radians into degrees, sort of the opposite of the question above, I simply put my lines on top and I say 5 pi over 6 radians, above the radians, unknown degrees, and when we cross multiply this 180 up there, we have 180 times a 5 pi over 6 divided by a pi. You could cancel this out with fractions, and there'd be a 180 that cancels with a 6. The pi's cancel, and you really do end up with a nice number, 150 degrees. Now, understanding what 1 radian is, we'll convert that in just a moment, but it's kind of nice to be able to estimate. Now, not everyone's going to understand this initially, but if I were to say a full rotation is about 2 pi, 2 pi is about 2 times, I'm going to say about a 3. That's very close to a 6. So a full rotation is about 6. A half rotation is about a 3. A quarter rotation is about 1.5, which makes 3/4 of a rotation about a 4.5. At least it's pretty close to that. So if I were to say how much is 3 radians, you know that it's about half a rotation. Technically, 3 rotations is just a bit shy because a full half rotation is 3.14, so 3 is a little bit less. Regardless, if I were to ask how much is 1 radian, I'd probably say it's somewhere around there. That's about 1 radian. Maybe it's about 50-ish degrees, 60 degrees, somewhere around there, but let's actually convert to find out. If 180 degrees is pi radians, then 1 radian is how many degrees? Pi slides up here, and whatever pi divided by 180 degrees is, I have that backwards. We're converting 1 radian, the 180 slides up here. So 180 slides up here to get the x by itself. We're doing 180 divided by pi, and in our calculator, 180 divided by pi is about 57 degrees. So that's how much 1 radian is. Sometimes you're going to see radians with a pi in it. Sometimes you're just going to see a number. And those feel a bit frustrating because you've just been told that pi over 4, pi over 6, these numbers with pi in them are radians. But sometimes your values can be decimals, sometimes they're whole numbers, and sometimes they have a pi in them. And that's just the way the radians can be. They can be exact, they can be rounded, they can be whole, they can be decimal. So as a bit of a refresher of last year's angles and standard position, you talked about this structure where there's an initial arm that sits on the positive x-axis, and we call this again the initial arm. We'll label this. Now what happened is, from this initial arm, you had an arm that rotates around, and this stopped somewhere. Let's just say that it rotated until about here. This is where it stops. This is called the terminal arm, where the terminal arm defines an angle. This angle from the initial arm to the terminal arm is called the angle in standard position. And this standard position can have an angle that's quite large, it can be quite small. So it might be 10 degrees, it might be 130 degrees, it might be, as it keeps rotating, 720 degrees. But what is defined from this terminal arm is a smaller angle. I'm going to call this theta for the moment. And this smaller angle is called your reference angle. The reference angle is the angle from the terminal arm to the closest x-axis. So depending where the terminal arm ends defines the position of your reference angle. It is important to know how this reference angle can look depending on the quadrant or quadrants that you end. So let's look at a terminal arm being defined and where a reference angle might be. So if I said 150 degrees, we would travel past the 90, not quite past the 180, and say we're somewhere in here. This is 150 degrees, and what I'm asking us to do in this section is to draw the following terminal arm given and convert your answers from the given units to determine the reference angle. All we're going to do is work on the reference angle for the moment. And so if we figure out what's the smaller angle between the terminal arm and the closest x-axis, our math might look like a 180 degrees, take away a 150, should give us that smaller angle, which in this case is a 30-degree angle. 5 pi over 6, that is actually the exact same position. In my brain, I'm thinking 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6 is a little pi over 6, 30 degrees shy of a full 180. So how much is left over? You might say, well, I've got a full 180, take away 5 pi over 6. And what's left over is 6 pi over 6 minus 5 pi over 6 is a 1 pi over 6. So this is the exact same question given in a different unit. You can also have negative angles. Negative angles are traveling in the clockwise direction instead of in the counterclockwise direction. So a negative 60 degrees is defined here. Negative 60 degrees is right here. In standard position, this would be 300 degrees. So technically, negative 60 degrees and 300 degrees are actually the same position. They're the same terminal arm location. But as a reference angle, our answer has to be between 0 and 90, and we're going to answer with 60 degrees. The angle between the terminal arm and the closest x-axis is 60 degrees. The negative 60 is only referring to a direction downwards, clockwise, not up. The 2 pi over 3, and I'm actually going to change this example and say 240 degrees. And so if we say 240, we travel around, until we are just a few degrees shy of this one. So this is 30 degrees shy of 270, but the reference angle is defined from the terminal arm to the closest x-axis. So in this case, theta is 180 degrees, but we could add, this is, maybe we should take 240, take away 180, and what should be left over is our theta, which in this case is 60 degrees. So your reference angle 60 and 60 matches, and these two terminal arms share some information, but they are in a different angle and standard position. Now I mentioned the idea already about these angles that can be in the same spot, this -60 and the 300. These are called coterminal angles. Coterminal angles do have the same location of a terminal arm, but they have moved from their position. So we're really not saying convert to a different value. 5 pi over 6 and 150 are not coterminal. They are the same angle, different units. But a -60 and a 300 are talking about different rotations to the same place. Those are considered coterminal. So as an example, can you determine another angle that is in the same position as -1 pi over 2, 2 pi over 2, -3 pi over 2? I would say a nice easy one is to say pi over 2 ends in the same spot. How about 5 pi? Well, again, drawing this out, 5 pi might be traveling 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. This is in the same spot as if we had just said pi. 40 degrees, that's in the first quadrant. We could get this by saying a few things. We could say, let's travel a full 360, add a 40. So we could say 400 degrees. Or maybe we travel in the negative direction and say -360, but just back off 40. Or maybe we could have said -320 degrees. Similarly, we have a negative angle, -330. So -300, not 60, but -330. So this is 30 degrees shy. Maybe we just say it's the same as 30 degrees. Now these are very specific about one angle as an answer, but because rotating could continue, rotation doesn't end at 360 or 720, they keep going. So in a general form, we can talk about the infinite nature of rotation. So if a given angle has an infinite number of angles coterminal with it, one expression can represent all locations. So if I were to say 360 and 720, and every multiple of 360 in the positive or negative direction, I could say that the angle 0, or 360 or 720, is really every multiple, every 360 degree multiple, just multiplying by 0 or by 1 or by 2 or by 3. Or so maybe we'll say every multiple of 360 where we're multiplying by not a decimal or a fraction, maybe by an integer. So if I multiply 360 by 0, I get 0. If I multiply 360 by 1, we get 360. If I multiply it by 2, we get 720. By doing negatives, we just travel in the negative direction, and we can talk about all angles